Hello everyone. Good afternoon. My today's topic is SDB, efficient Ruby stack scanning without the GVL. When you see this title, you might wonder when creating another stack profiler, Ruby already has dozens. And many of them work pretty well in their cases. Why should we create another? And you might be weird why we want to scan the stacks without the GVL. How could we do this? I will answer all of those in today's sharing. And in my today's sharing, I will describe why I designed a new stack profiler. Then I will describe how I designed it. After that, I will discuss how to scan the Ruby stacks without the GVL. Let me answer the first question, why a new stack profiler? To answer this, we need to see how we use instrumentation and the stack profiler. We know people use the instrumentation as the default solution. And we insert the code around the function we want to measure their latency. No matter through an instrumentation library, or such as the datadog or Nurex, or we can insert those code by ourselves. But the thing is, we can't insert the instrumentation code to all the functions. That means cost too much. No matter the manual effort or the overhead of those instrumentation code. So for those functions do not have those instrumentation code, we can't know their latency. They are blind spots of our instrumentation. When the performance issue happens during those blind spots, we may enable a stack profiler to see can it help us. So you see here, first we have instrumentation and we know it may not work. Then we use another tool to work as a complement. But my question is, why not we just use one tool? We just use the stack profiler in the first place. And doing this, the benefits seem to be obvious. You see, the stack profiler is implementation agnostic, and it has less blind spots or no blind spots. More importantly, it doesn't require us to write the instrumentation manually, and it means less effort. But in practice, this seems not happen. Maybe happen really well. I think there must be several reasons. First, I think most stack profilers are designed for average latency. For example, many of the profilers use the 10 milliseconds as their sampling interval. That means if a request takes around 50 milliseconds, those stack profilers can only gather 5 samples. The 5 samples can't say much about a single request. So I think they are not enough for any specific request. However, the instrumentation works on the other side. Even they have blind spots, they can detect any request state. So that's the good part of the instrumentation. Another issue of existing solution is they may use the high CPU. If a performance tool may consume more than 10% CPU, we may hesitate to use it. More importantly, because existing solutions need the GVL. As we know, the GVL when the stack profiler holds the GVL, the Ruby application can't do its work, so it slows down our Ruby applications. So I think if we want a stack profiler that can replace the instrumentation, we can use a stack profiler only. This profiler must fulfill several things. First, we should reduce the sampling interval from 10 milliseconds to 1 millisecond. And we should keep the CPU usage as low as possible, maybe less than 5 or 3%. And more importantly, we should not use the GVL when we scan the stacks, as no one wants to slow down their applications. Okay, after we know why I want a new stack profiler, I will discuss how I designed it. We can check the general solution first. Most typical stack profiler will has 2 parts. One is the signal trigger, and another one is the signal handler. The signal trigger sends the signals to the application threads regularly, maybe every 10 milliseconds or 1 millisecond. And when the application threads receive those signals, it invokes the handler. And in that handler, it scans the stacks and synchronizing, or maybe do some analyzing. For the signal trigger, you see it actually just does some simple job. It just sends some signals. And we can release the GVL in the signal trigger. So for a signal trigger, its job is quite simple, and there's not much to say about it. So let's us check each element of the handler. One component of the handler is the analyzer, which aggregates gates we collected. Yeah, that's because the stack scanner only can know which functions are on the stacks or which functions are during execution. And we need another component to calculate or infer those functions latency, average latency. Yeah, that's the analyzer. And after that, we may need the analyzer to convert the data into other formats. I mean, maybe you want to present the data as a flame graph, or have some text summary about each function's average latency. So that's the thing. Actually, the analyzer does the heavy work. Yeah, but for it, we can do the lazy and offline analysis. Yeah. As a default stack profiler, it can collect a lot of symbols, but only some of them we are interested in. So we can only analyze those symbols we think relate to our performance issues. So we can perform lazy analysis that can reduce a lot of work. Yeah. Another thing is our design goal here is to reduce the impactation on our production environment or online servers. That means we can pull the data to our local machines or other machines, so it doesn't impact our online servers. Yeah, for the analyzer, its solution is to perform lazy and offline analysis. The next component of the handler is the symbolizer, which converts memory address into human-readable symbols. Yeah, the stack scanner only can gather the function or methods addresses. So to understand them, we need to convert those addresses into method names and other details. So the analyzer. Yeah, but we know for any given Ruby applications, they only have limited set of methods. That means if we do not convert a method address to symbols repeatedly, that means its work is manageable. So for a symbolizer, its solution is to catch the translation results. Okay, after those two changes, our architecture looks like this. You see the stack scanner and the symbolizer only gather state and log them into file. And after that, we can perform the analysis when necessary. So that's the offline analyzer. Actually, after those two changes, the stack profiler should have much better performance. However, there is still one last element, the stack scanner. The stack scanner travels and collects data regularly, maybe every 10 milliseconds or 1 millisecond. Yeah. A typical live stack can have 100 to 200 frames. For a modern CPU, it can run very fast. That means if we scan a 200 lines array, it doesn't take much time. So that for us, it means if we do not scan the stacks in an extremely high sampling rate, this part work is light compared to the other two components. But the existing solution is not ideal because they use the GVL. That means when the stack scanner holds the GVL, our application can't do their job. It blocks our application's execution. So it slows down our applications, and it limits scanning frequency as well as accuracy. Yeah, so let's go to the next section. How to scan the stack without the GVL. Yeah, let's recheck our stack scanner. The stack scanner reads the active frames and record those frames information into a file or into the memory. And at the same time, the Ruby VM will update them. I mean, push a frame onto the stack or pop a frame out of the stack. More importantly, the frame is a Ruby internal structure. We know the GVL is used to protect all Ruby objects. Yeah, so it seems that we must use the GVL. But if we look at it closely, it's not entirely true. Yeah. To answer this, we need to check the duty of the GVL or analog. Yeah, here is an example. There are two threads. Both of them share the same object, the instance of the linked list. And the thread 1 wants to free the last element of the linked list. And the thread 2 at the same time wants to read it. Unfortunately, the thread 2 first holds the tail element, the host element's address. And after that, the thread 1 frees that element. Then the thread 2 wants to read it. As the element has already been freed, it means it will cause segmentation fault. To solve this, people use the log generally. Yeah. You see, the log group things together and it sequences critical sections. That means each section can't happen at the same time, so there's no such issues. Yeah. If we look at it closely, we can find out one job of the log is to group the instructions, several instructions, make them as a whole item, a whole unit. It's atomic. But here my question is, what if we only need one single instruction? The instruction itself can guarantee atomic. Do we still need the log? Yeah. Okay, the answer is no. We do not need the log. For example, there is a counter. We can read and write it without any log. Yeah, in my program, we may see some outdated value, but no corrupted data. So, for example, that means the CPU 1 has already updated the value to some number, and after that, the CPU 2 wants to read it. It may read some old value, but it will not read some invalid or corrupted value. The value count belongs to different numbers. So for a counter, the log is not necessary. That's because the 64-bit aligned memory, read and write, are atomic. That means the read or write can happen fully or not at all. There's no intermediate state. This feature is guaranteed by the hardware. Yeah. After we know this, we can check the SDB stack scanner. Actually, a stack scanner only depends on one single field, which is ISEQ. It holds the address of the iSequence structure. You can consider this structure as the internal representation of the Ruby methods, yeah, for simple. Yeah. And the ISEQ field is a 64-bit aligned memory. That means we can read it safely without any log, without the GVL. So that's the foundation of why we can read the stack without the GVL. Yeah, but the formal step only guarantees that if a frame is alive, we can read it. Now we need to guarantee that we only read the live threads. Yeah, we know Ruby uses the stack to store those frames. And the stack is a serial array. This array is allocated when Ruby creates the threads and will be freed after the thread finishes its work. So when a thread is alive, its frames array must be valid, so it's safe to read it. Yeah, here is the implementation. It's quite simple. We can wrap the code around the thread block. It's for synchronizing with the Ruby VM and the stack scanner. It just tells the stack scanner, okay, there's a new thread. You can start do your work. And after the thread finishes its work, it just tells the stack scanner, okay, this thread will die. You should not scan it anymore. Yeah. After this, we still need to consider how the stack scanner works with the Ruby GC. That's because in the stack scanner scans Ruby memories, we need to know how Ruby manages its memory or how its GC works. One duty of GC is to free the inaccessible objects. For example, after a real request, all its local objects are not useful, so we can release it, and its work is done by the GC. But we know the SDB stack scanner only scans live threads, so it's safe for here. Another duty of GC is memory compactation. We know Ruby can enable the auto compactation, and in this function, in this feature, it moves objects to different locations. As the SDB needs to scan the Ruby memory, if the memory, the memory has been moved to other location, it will cause errors. But the good news is the Ruby VM doesn't move all the objects. I mean, some objects, when they are allocated, they will not be changed to other place. And the SDB stack scanner only depends on those objects. I mean, the execution context and its stacks. So that's why it's safe. Yeah. But if you want to read some movable objects without the GVL, there are several options. You can read the immutable ones and do not read them during any GC phrases, or you can insert some logs for them. To summarize, the SDB only reads the ISEQ field, and this operation is atomic. And the SDB synchronizes thread state with the Ruby VM, so it never reads any dead threads. And as the SDB only depends on the fixed objects, so it works well with the GC compactation. So that's why SDB can scan the stacks without the GVL safely. Okay, we know the implementation, so now we need to discuss the databases of thread safety. If you look at it closely, you see the Ruby VM updates the stack, while the SDB reads it without the lock. So that means the databases can happen, or it has thread safety issue, but I haven't solved it. You can see several similar tools have this issue. For example, the RB-SPY, PY-SPY, both of them offer the non-blocking mode. That means in that mode, it has this issue. I mean, it's not thread safe in that mode. Or you can see the Java async profiler. Use some functions doesn't guarantee the atomic, so it has the same issue. So I believe in practice, the databases is not a thing must to be solved. That's because for a stack profiler, actionable is far more important than strict correctness. You can imagine when the stack profiler can yield some wrong results only when those functions are extremely high. But our stack scanner are for detecting the high latency functions. So those extremely high functions doesn't matter to our interest. So I think actionable is far more important than strict correctness. This trade-off happens in many areas actually. For example, the eventual consistency in database or the RCU in operating system. Yeah. However, if you still want to solve this, we have solutions. Yeah. For example, the LDB, which is a paper published in SDI 2024, it uses a generation number for concurrence control, so it's still resolvable. Yeah. Yeah. After we have all of this, I mean, we have this implementation, we know how it works. We need to do some tests to see does it works as we expected or not. Yeah. So I did several evaluation. In my evaluation, I focus on two things. One is the overhead. I measured the SDB with a GVL-based solution and run several stack profilers on a Rails application to see the overhead of those tools. Additionally, I have sampled one single request to see how much information can be gathered by the SDB. The first evaluation is on an AWS machine. Yeah, I used a simple script to do some calculation. I compared the SDB, the no GVL solution, and a GVL-based solution. I run them in different sampling intervals to see how the different sampling intervals impact the execution time. I mean, how they impact our performance. And the GVL-based, I didn't use any existing solutions for the GVL, yeah, because the existing solutions does too much work, making it hard to isolate the impact of the GVL. So I wrote a simple one. It only does some bare minimum job for better performance. Yeah, and here is the results. You see the x-axis is the sampling interval, ranging from 1 millisecond to 1 microsecond, and the y-axis is the execution time. The larger means the stack profiler impacts the script much. Yeah. The blue line represents the GVL-based solution. You can see it clearly. When we decrease the sampling intervals, the execution time increase sharply. So that means that demonstrates how the GVL impacts our performance for a stack profiler. On the other side, you see the GVL-based solution, even we decrease the sampling interval, it doesn't change the execution time. That means it doesn't impact our applications. Yeah, that's the first evaluation. Yeah. After that, I did an evaluation on the Rails application, because many Ruby use the Rails web frame, so it represents the production usage. Yeah, the real use case. Yeah. I picked the homeland, which is the most famous Ruby forum in China. Yeah, and it's written by professional programmers. So I think this application is quite representative. So I run it on an AWS machine and use different DB, use different thread sender. And here is the setup. And I picked the sampling interval as 1 millisecond. The reason is the homeland, its latency is larger than 30 milliseconds. So 1 millisecond sampling interval is quite enough for it. So I think it's okay. And the measure method is quite simple. I just run the homeland without any stack profilers to see its latency and its CPU. After that, I run it with one single stack profiler and measure the CPU usage and the request average latency again. And the overhead of this stack profiler is the difference between those two tests. So that's the method. Yeah. And here is the detail of those stack profilers. I will not read them. Yeah. And here is our result. You see, there are two groups of bars. The first group is the average latency increased. I mean, after we enabled the stack profiler, how much average latency has been increased. Yeah, and the second group of bars is the CPU usage, how much CPU those stack profiler usage. Yeah, we can see the green bars belong to the SDB. It only increased 0.5% average latency and use less than 3% CPU. I think it's quite good for most applications. Yeah, even for some large scale of Ruby servers. Yeah, and the blue bars represent the RB spec. It doesn't increase our latency, but it uses a lot of CPU. I guess it may because it needs to read the memory from other process, and it may does a lot of work in its stack profiler. Yeah, it needs when we enable a RB spec, it calculates the average latency dynamically, so it could cause a lot. And the next bars belong to vanilla 1.0. Yeah, it doesn't use much CPU, but it increased 10% of our average latency. I guess it's not good for a default solution. I mean, if we enable a stack profiler and it increased 10% latency, maybe we will not use it like this. Yeah. And to be clear, the vanilla is 1.0. It has several newer versions. I haven't tested them because time reason. But I think the newest version of vanilla could have much better performance than this test. And I must to say, both the RB spec and vanilla are quite good, useful stack profilers. You can imagine if we just want to enable it occasionally, the 10% of CPU, the 10% of average latency increase, it doesn't that matter. And for the RB spec, if we change the sampling interval from 10 milliseconds to 1 millisecond, its CPU usage is reasonable. However, the SDB is targets for enable by default, enable always. So it must use low. It must make the impactation as low as possible and use the low CPU or other resources. So that's the difference. Yeah, here is the one samples of one. Here is the samples of one request. You see, it can collect a lot of information. Yeah, it collect a lot of methods, and actually, the whole things it collect is very large and can't analyze. So I just cut maybe 10% of the whole image. So that's the result. I think it's quite enough for most cases. Yeah. Last question I'd like to answer is, does the effort pay off? Yeah, the engineer is never as simple as to find a better solution. It's about the payoff. I mean, does it deserve or not? Here is the facts of the SDB. Its stack scanner and synchronizer do not have much length of code. It have less than 1,000 lines. So I think its implementation, its code size is quite small. But to read it, we need to understand the several things under the hood. I mean, we need to understand the GVL, the GC, the sequence, and a little bit about the low-level concurrency. After that, we need to make the design and the trade-off. So, to be honest, the no GVL introduce additional effort. Yet, different people may have different standards about does this effort deserve or not. So I can't answer it directly. Yeah, but for me, this journey, I mean, developing this stack profiler is quite interesting. Even it's challenging to learn a large complex system. I mean, the Ruby VM, and it's much more harder to debug in it. But I learned a lot, so it's interesting and memorable. Yeah. For the current state, I believe the SDB is still in an experiment state. It's not production ready. Because it only supports one Ruby version, yeah, I will support more in the future. Another thing is I want to rewrite the synchronizer without the eBPF. Even the eBPF is the common solution. Yeah, a common solution for observability. Several libraries use it. For example, the Golang OpenTelemetry implementation. But I think it's an unnecessary dependency, so I plan to remove it. And additionally, I'd like to integrate more Ruby internal events. It can help us detect the tail latency more easier. So that's my plan. Yeah, this part is the related work. If you are interested in this field, you can check those things. But due to time reason, I will not cover the detail. But I'd like to point out one thing. People devote quite a lot of effort for making the performance debugging more easier. No matter reduce the effort of manual instrumentation or the effort of root analyzing. Several previous works have proved that if we can collect as much information as we can make the root cause analyzing super simple. But it also means it introduces a lot of overhead. The SDB wants to explore that direction, but it wants to achieve some balance. I mean, collect as enough information as we can, but keep the resource usage as low as possible, so it can make it practical and really be used in industry projects. Okay, to conclude, a stack profiler can release the GVL, and I think it is beneficial. The SDB provides high sampling rate with low performance impactation and CPU usage. And I believe due to those things, I believe the SDB has the potential to be a default observability solution. Okay, that's my sharing. Thank you everyone. And the project is available at here. Yeah. Okay, there's some. Feel free to ask questions. I hope I have described it clearly. Yeah. Thank you. Okay, feel free to reach out to me if you have anything, if you're interested in this one. Yeah. Anyone have a question? Okay, if we do not have questions, I have one little thing. Yeah, I have brought some synthetic Ruby. Yeah, it's true Ruby, but a synthetic Ruby as a small gift. So I think as a Ruby programmer, this gift is quite interesting. So feel free to reach out to me, and I will offer some. But I haven't brought much. Yeah, that's all. Thank you.